Okay, great. So while those talks were pre-recorded, many of the authors will be at their posters or on the Slack or here on the webinar. So do feel free to reach out to follow up with questions on their work. And now we will be hearing 3 live contributed talks from some outstanding papers that we received. So the first will be from Eduard Chelebian, who is a PhD student at Uppsala University in Sweden, working with Carolina Walby. Today, he'll be presenting work that he did while visiting the Radboud University Medical Center in the Netherlands. Take it away, Edward.
Can you hear me?
Yes, though we're seeing a white screen.
Yes. Now it should work.
Perfect.
Great. So yeah, thank you very much for the invitation. And yeah, I am Edward, and I'm a PhD student here at Uppsala University in Scilab Lab in Sweden. And as you said, yeah, I did this work during a research visit at the Radboud University Medical Center, which is in the Netherlands. So I will start this work by motivating a little bit this project. So as many of you know, supervised training often requires big amounts of data, which needs to be annotated. And especially in the case of medical images, it's pretty hard to obtain these annotations. It also requires long training times and computational resources like graphical processing units or GPUs. And some previous work proposes active learning or human-in-the-loop strategies to deal with this problem. But if you want to use deep learning approaches, one often requires having both interactive support and also GPU support at runtime, which is something not everyone has. And instead, when we want to do some kind of deep learning, more often than not, the computationally heavy things are done in the GPU high-performance cluster. So based on this realization that most of our environment work like this, we propose to decouple the problem by pre-computing deep learning features in a remote manner, so we can still leverage their power and then only use them locally to cluster them based on small annotations, which is computationally very cheap. So this is a general overview of the complete methodology that then I will explain part by part. And I will try to keep it light. So if you're interested in the more technical details, please refer to the paper. But in general terms, we have a remote part where, as I said, all the computationally heavy things happen, and a local part where, based on seeds planted by an expert and via a modification of k-means clustering, which is very cheap, we will obtain a full image segmentation. So let's dig into the 2 parts separately. So whoever has already worked with whole slide images might be familiar with this part, but just in case I will go through it quickly. So when you have medical images, they are usually thousands by thousands of pixels. So dividing them into smaller tiles is pretty standard. I show here a small animation to clarify what do I mean by overlapping patches. And also, so you see what the dots will mean when we go to the full image. It's just the center of each patch. So once you have these individual patches, you can embed them, passing them through a convolutional neural network, and then get the penultimate layer activation as a representation of the patch. And this is how it looks like. As you see, circled is not the last layer, but the penultimate layer. So here we're faced by the first choice, which is the architecture that you choose to represent your patches. In our work, we tried with different depths of ResNet, so ResNet 18 and ResNet 50, and you see that they yield different length of features already, 512 and 2048, a number of features, and they will be very different because of the number of operations they go through. Yet another choice is the pre-training, so the actual weights that each patch will go through. So a pretty common choice here is to use a network with weights pre-trained on ImageNet, but ImageNet is a natural image database. So some authors have already pointed out that this might not be ideal. So we also will compare with a more recent approach, which is to use self-supervised learning. In this case, the contrastive SimCLR framework, which is basically based on maximizing the agreement of the annotations and the original patches. And we try to do this with the data set that we are working in, and also a data set that weights that you can find online, which are based on the paper I cite here, which uses 57 histopathology data sets. Then let's go back to the full picture and see what happened, which basically was dividing the image into overlapping patches, then embedding them. And then we get a matrix of embeddings in our high performance cluster or wherever we do this. So we now locally only download this matrix. And we go to the local part, which will be the interactive part. And yeah, you remember already the dots I mentioned before. This was the center of the patches. That's what you see overlapped, like these black dots on top of the image. And to the right, I just showed the reduced UMAP space of the representations. And a little disclaimer here is that this is shown only for visualization purposes. We cluster actually on the full space. And the visualizations are made by the tissue map software developed at our group. Anyway, we would have the expert plant some positive or cancer seeds, in our case, the red ones, and some negative or benign seeds in the green ones here. And in our case, the seeds were randomly generated, so we could scale up the project. But of course, we would have an expert doing this. And the iterations that I show next happen instantly. They are very fast, but just to show what our method does. So when we run it, basically we use the seeds that we have and the complete embedding space. And we run a seeded k-means, which is a fairly classical method. Works exactly like k-means, only you choose the initialization of the first centroid based on the seeds you have. And as you can see, all positive dots in this case ended up correctly clustered, which is not necessarily obvious because this is not a constrained clustering method. But some of the negative dots in this case are misclassified. So what we would do is we eliminate the negative part and we keep it, and we recluster the positive part, the red part, with the seeds that we have left. So this is the result of doing this. And the new green part will be the merge of the old green part and the new negative class. So you can see that we're just reclustering the positive part by trying to get all the seeds in their correct cluster, or at least until a classification metrics that does not improve. So in this case, we still can go one iteration more. And then we have this final result where all the clusters, all the seeds are in the cluster that corresponds to them. And something I need to mention is that even satisfying this condition doesn't guarantee a good result, because we are very dependent on the actual feature space. But the way we compared here is we take a look at the result after the iteration stop and the actual ground truth that we have for this data set. And as you can see, it's pretty close. And there are some small errors that could be fixed by for post-processing. But yeah, we decided to show here the raw results. And a small fun thing we can do is, additionally to reducing the space to 2 dimensions for visualization, we can reduce it to 3 dimensions and then interpret those as RGB color channels. And you can already see that the green parts in the center were already kind of further in color space. And this can be done just before running your experiments to check for feasibility, but it's purely qualitative, just some small little thing. So for evaluation, we use the digest path dataset for colorectal cancer segmentation. And here we have images of whole slide images of H&E stained slides. And then we have the ground truth cancer segmentation already made by a pathologist. And these are the results. So the colors represent different combinations of feature extractures and architectures. And the x-axis shows the number of seeds per class planted by the pathologist. So in the example before, I showed 3 seeds per class, so 3 clicks. We see that even one correctly placed seed can already yield pretty good results because you're just initializing your clusters. And as for the inferior results here, we found out that more often than not, they are due to artifacts that could be fixed by post-processing. But again, we have already fixed this, but I wanted to show the same result as in the paper. And we can still see here how superior self-supervised weights are to ImageNet, which I feel is not a result we always find in the literature. So we can discuss about this a little bit later. And also, one could argue that the green box plot here, so using your own data for for pre-training the contrastive learning. It's not something you can always do, especially in a clinical setting. So seeing an open source model work so well is pretty promising. And here I show some examples included on the paper also of results. And as I was saying, some post-processing really helps to get a much better segmentation here. But something you can already see in the original images is how different the stainings are, the colors are. And this method is dataset, and I would even say task agnostic. So these big staining differences that are usually a big problem are not a bottleneck in this kind of methods. So as I promised, some technical discussion here. In addition to having this segmentation tool idea, there are some technical contributions, such as this framework can be used for comparing the features extracted by different network, because it has been shown that when you do transfer learning and then when you retrain, the contribution from retraining can blur a little bit the effect of the actual features that you had in the beginning. So doing it this way is a less biased way of comparing weights. And also about generalization, as I said, when you fine-tune and you update all the model parameters, has been shown that you can achieve worse accuracy. So doing this feature extraction approach, when you don't really retrain the whole network, is more robust. So some limitations, as I mentioned, you can get incorrect solution even by satisfying the restrictions that we put. The evaluation and benchmarking here can be a little bit hard, but we're already working on that. And the post-processing step that we already added really improves the segmentation results. Right now, we only work on binary classes. We would like to extend this to a multi-class problem. And one of the reviewers pointed out that even separating remote and local makes it easier to use, maybe, but it's really important that the remote part, this feature extraction part, is really straightforward for ease of use. So finally, a real quick demo I made a couple of days ago, how the progress looks right now. So this is one of the images in the challenge, and overlaid, I show the ground truth, this red part. Of course, pathologists wouldn't have this, and they would have to zoom in the multi-resolution image and find the cancer regions. But by building an interactive tool, we can already see how this could be used by correcting and easily adding some extra seeds and running it again, because the calculations are instant. As you can see, just click, and this result is not very satisfactory, but then I hope you're seeing the GIF. You can add a couple more seeds, and the result gets much better. So thank you very much for listening. Thank you also for organizing this workshop. I think it's very nice. And please connect on Twitter and on LinkedIn if you would like to continue these discussions.
Great. Thank you so much, Eduard.